Okay, welcome to lecture here, final one of the season. We will get started here in just a second, continuing on with chapter 11, I think it is. Okay, so we'll get started. And again, we've been talking about kinetics in this chapter. And remember, kinetics basically describes how fast or how slow reaction will take place. We saw a couple of things. We saw a rate expression, which you could use to relate both the reactants and the products to what's going on. So again, if you have an equation, you can do something like the rate equals minus 1 over A. If this is A, this is B, that's C. The change in concentration of A over the change in time. You could also do the same relationship for our other reactant. You could set it equal to each other there, that minus 1 over B, change in concentration of B over change in time. And that would equal 1 over C, change in concentration of C over change in time. And here we do use, hopefully others are coming, hopefully. We are looking at the negative here on our reactant side, again, assuming that we are decreasing with time. As this reaction is taking place, our reactants should go down. Well, on the product side there, we should be increasing with time, which is why, again, it is positive here on the other side. So we can use this to determine, there we go, get some people in. There we go. All right, a few more people. There we go. All right, so on the product side there, we would assume that it's increasing with time as we have the positive there. And again, we do 1 over the coefficient, as we talked about last time, to basically take care of the stoichiometry part of it and the stoichiometry relationship. And again, if you sort of do that 1 over the coefficient in the balance equation, that'll take care of all that multiple relationships that you need. So the rate expression is a nice way that you can basically figure out what's going on in the overall reaction. You can figure out the average rate. And again, you really just need one piece of information, either how the products are being made, the rate of a reactant, the overall rate. You just need some type of information about the reaction that's taking place, and you'll be able to basically figure out how everybody else in that reaction is changing. Then we started talking about sort of what is referred to as the rate law, and the rate law is sort of where we finished up on here. And the rate law has generically looks something like this. And again, if we wrote the rate law sort of for the reaction that we have on the right there, or left, do X's, get them nice and big there. One thing about the rate law, as we talked about towards the end as well last time, is it does only involve reactants. So when you write a rate law, it's just the reactants that are involved, no products in the rate law. We also have the X and Y, which usually aren't that big, but the X and Y are what are referred to as the orders. And there's sort of the way that, sort of proportional wise, these guys are reacting with each other to maintain a specific rate for a particular reaction. Now, X and Y are not the coefficients that you find in the balance equation. They do come from experimentally being found, and that usually means that we will end up with essentially a table in these type of problems. So you usually end up with a table in the problems, and that table will contain several pieces of information. It will contain basically usually the concentrations of your reactants, and then it will also contain sometimes what is referred to as the initial rate for each of the experiments that are done. And you can mathematically sort of solve for the orders. And one mathematical approach to it is really just picking two entries where you take the rate 2 over the rate 1, and that equals k times a to the x and b to the y over k a to the x and b to the y. And when we say rate 2 and rate 1, as we talked about last time, again, we're not talking about necessarily that you pick the first or the second entry there in the table, but you basically just pick two entries. So I think we just did one at the end last time here. Let's take a look. Maybe. There it is. So again, this is a common type table that you find in kinetics problems. Again, you have the concentrations of your reactants. You also have the initial rates, and basically you have like experiment 1, experiment 2, experiment 3, maybe even more than that in terms of experiments. And when we go to this table, what we're looking to do is really minimize the amount of unknowns that we have. So what that means is typically what you want to do is find two entries in the table where one of the concentrations, if you just have two reactants, where one of the concentrations remain constant while the other one varies. So like we saw last time here, if we look at experiments 1 and 2, the concentration of F2 remains constant at 0.1 for each of them, and the concentration of ClO2 will vary for each of them. And that's sort of what we did in this calculation over here. And again, that's that rate 2 over rate 1 sort of formula they just put up there. And typically, if you take the entry that has the larger rate on top, it usually will give you like a much nicer kind of whole number usually. And again, you can divide out the rates, which in this particular case gave us 4. The rate constants, we don't know what it is at the beginning, but they will cancel each other out as they are a constant value. The x is here as well. We don't know what it is, but it should be the same, so those will cancel. And that gave us this guy on the end here, the 0.04 divided by 0.01 to give us 4 to the y. Again, y would equal 1 in this case. Once you've done that, just like we did in this example, we then would want to keep the other concentration constant, which is the ClO2 in this case, at 0.01 and vary our F2 and basically do the same calculation. And as we see here, and as we did last time, what we end up getting again is those experimental orders. And once you have the orders sort of calculated, that then will allow you to do what we finished up on, which is calculating the actual value of the rate constant. So once you figure out the orders, you can then go back and solve for K in this rate law like we have down here. And once we solve for K, we basically can put in the numbers and solve for the actual value of K. And to solve for the value of K, we essentially can choose any entry in the table we like, as long as we keep all the values together in that entry. We could choose entry 1 in that previous table, entry 2, or entry 3, and they all should give us the same rate constant. And we sort of ended up here just, again, talking about the rate laws that, again, the orders that we have in the rate law are not exactly the coefficients in the balanced equation. So you shouldn't just take those coefficients and use them. As you can see here again, the ClO2 has a coefficient of 2, while in our rate law, it actually has an order of 1. All right. So here, if we look at this, the rate equation for this reaction of NO is the rate equals K NO times O3. If the rate is 6.6 times 10 to the minus 5, when NO is 1 times 10 to the minus 6 and O3 is 3 times 10 to the minus 6, calculate the rate constant. So again, here we can, this would be almost like what we did at the very end of that last example. We actually, in this case, have the rate law given to us. And what we know is, again, not needed to be written, but it is 1 for each of these, which means the overall order of this reaction is a second order reaction. So remember that if you take orders for each of the individual reactants and basically add them together, that will get you your overall order for a particular reaction. And since we do have our completed rate law, we just need to solve for K. K in this case would be the rate divided by NO times O3. And since they gave us those values, we would put it in. So we got 6.60 times 10 to the minus 5 molar seconds divided by our NO, which is 1 times 10 to the minus 6 molar, and our O3, which is 3 times 10 to the minus 6 molar. And if we put all that into our calculator here, hopefully correctly, looks like we end up with something like 2.20 times 10 to the 7. Just make sure I punch that in right there. Didn't miss anything. And in terms of units, when we look at the units, the molarity on top here will cancel out with one of the molarities on the bottom, and that will leave us basically 1 over molar seconds. And in terms of units, those are the typical units that you see associated with a second order reaction. So you actually can a lot of times determine the order of a particular reaction just based on the units that you see for K. And sometimes in problems, they actually will not tell you the order of the reaction, but they will give you the value of K. And based on those units, you do need to know how to sort of determine what order you're looking at. And we'll see a little bit more of that a little bit later on. Any questions on that there? All right, so here's one with a table. So why don't you take a couple minutes here and why don't you determine the rate law and the value of the rate constant using the information that you find in this table. So take a couple of minutes here and see what you come up with, and then we'll talk about it. Okay, so let's take a look and see how we're doing. Again, just maybe remind everybody the approach here. So again, when you're given a table here and you want to find the rate law, what we're looking for is you can start with sort of the generic rate law, which would be the rate in this case equals K times, and again, it's just our reactants involved. So we'll take our first reactant to the X times our second reactant to the Y. And again, really the purpose of this table is to allow you to really figure out what X and Y is. And for most people, mathematical sort of approach is the best sort of approach, where we again pick two entries like we were just sort of talking about. And the goal here when we do pick those entries is that we want to keep one guy constant while we vary the other. So if we look at the table, we could see that in experiment 1 and experiment 2 here, the concentration of the S2O8 is constant, which means if we take our rate here, 2.2 times 10 to the minus 4 equals K times our 0.08 to the X, and that would be this guy right here, times our 0.034 to the Y, which would be this guy right here. So again, everything I just wrote was all from experiment 1. And now I'm going to basically put in everything here for experiment 2 all the way across. So the rate here, 1.1 times minus 4. K, here our concentration of this guy is constant, and we're varying this guy here. So again, we're going to do some math. So we're going to divide those two, and that is going to give us 2. As we talked about last time, the K value in each of these, we don't know what it is at this moment, but it is the rate constant, which implies that it is a constant value. Although, again, we don't know what the value of X is at this moment. We do know that it would be the same for both, which means essentially this guy here, and oops, apparently went backwards. There we go. So this guy here and this guy here would cancel out. And then if we divide these two here, I believe we will get a 2 to the Y. And again, if you want to get rid of both of them, if you can't figure it out, this one's pretty simple. You can pretty much figure it out. You could actually take the natural log of both sides and divide. And when you do, you will get Y is equal to 1 in this case. When you take the natural log of the other side, it will bring the Y down. Now, what we want to do is after we did experiments, basically 1 and 2, we then want to go back to our table and we want to find 2 entries where the other concentration remains constant and we vary our one that we held constant a minute ago. So looking at this table, we see that in experiment 2 and experiment 3 here, we have the same concentration for the I minus, while our S2O8 2 minus varies. So we're going to do the same thing here now using 2 and 3's information. Again, I'm going to take number 3 on top, which has a larger rate. And again, that just kind of gives you usually a little better number at the end in terms of a whole number. You could do it the other way as well. And again, everything I just put there is all from entry number 3. And then we'll take everything from entry number 2 on the bottom. So same thing here, we're going to divide, and this is going to give us 2. Again, the K's, we don't know what it is, but they should be the same, so they'll cancel. 0.08 and 0.16, when you divide that, gives you 2 to the X. And again, since we held this constant, it will also remain constant. And again, you can see here, X does equal 1 in this case. So that means that the completed rate law, now that we have the order, should be the rate is equal to K times S2O8 2 minus times I minus. Again, just like a lot of things in chemistry, if it is 1, you typically don't need to put it in there in terms of the exponent. You could just leave it with nothing there, and it's implied to be 1. We also know that the overall order here of this reaction is 1 plus 1, which equals second order. And again, that just comes from basically adding this guy and this guy together to give us the overall order for this reaction. And now that we do have that completed rate law, we can use the completed rate law to calculate the actual value of K. And if we do that, we would rearrange the rate law and we would see that K equals the rate divided by S2082 minus times I minus. And again here at this point, you could choose all the information for experiment 1, you could choose all the information for experiment 2, or you could choose all the information for experiment 3 and put them in there. So I'll just go for experiment 1. So that's going to give me 2.2 times 10 to the minus 4 molar seconds divided by, as I run off of my screen there, 0.08 molar times 0.034 molar. And if we do all that, looks like 8 point, we'll go with 8.1 times 10 to the minus 2. And again, in terms of units, molarity and molarity cancel, leaving us 1 over molar seconds. Looks good in terms of your answer there. And again, the units do match up, as you will see shortly, with what we have here, which is our second order reaction. And again, 1 over molar seconds is typically what you have in terms of the units for the rate constant for this type of reaction. Any questions on any of that part of the calculation? So again, here the goal is, to just have one unknown. So you want to keep things constant. If you happen to have had 3 reactants, you would want to keep 2 constant while you vary the third, and then obviously switch it around. Any questions on any part of that there? All right, so I think got one more here. Let's see how you do. All right, so again, same deal, a few more entries in this table. So see what you come up with. Again, looking for the rate law and also the value of the rate constant with the proper units. So see what you come up with. Okay, so let's take a look. And so same approach here. Again, we can start with the generic rate law. So again, just our reactants involve no products here in the rate law. So NH4 plus to the X, NO2 minus to the Y. Again, we want to pick two entries where one of them remains constant and the other one varies. We actually have 4 entries to choose from here. So I'm going to go for the first one here, 1 and 3. No, 1 and getting old here. We'll go with 1 and 2. Let's mix that up. 1 and 2 will keep the NO2 minus constant. So if we take the larger rate on top, which is entry number 2, we got 32.3 actually times 10 to the minus 7 divided by 10.8 times 10 to the minus 7. If you're curious where I got that 10 to the minus 7, it is right there in that table. And you want to make sure you don't miss anything like that. Otherwise, you're going to be off by a factor when it's all said and done. So our K, which will be 0.06 to the X and 0.2 to the Y. Again, everything on top comes from entry number 2 in the table. On the bottom is entry number 1 on the table, which would give us 0.02 to the X and 0.2 to the Y. So when we do a little dividing here, perhaps, we're going to end up with approximately 3, 2.9999. Our K's are going to cancel. This is going to give us 3 to the X. And again, these guys will cancel as well. Here we see X will equal 1 in that case. Now that we held our NO2 minus constant, we want to hold our NH4 plus constant. And now I'm going to pick 2 correct ones here. So we will go with entry 3 and 4 to do that. And again, taking the larger guy on top, which is number 4. And putting everything for entry number 3 on the bottom. And probably should put the number in there. That would be good. And when we divide our left-hand side there, 21.6 by 10.8, going to give us 2. K's are going to cancel. These again are going to cancel. And in this case, this will give us 2 to the Y, which means in this case as well, Y is equal to 1. We now have the orders for each of the reactants, which means the rate equals K times NH4 plus and NO2 minus. Again, the overall order here is going to be 1 plus 1, which again is second order. So once again, when we finish our rate law, we can now rearrange it and solve for K to get the actual value. And again, in this case, you can choose any entry you like from this table. 1 through 4 should give you the exact same K value. Again, you just can't mix and match, so you just got to use all the information for 1. So I'm just going to use number 1 actually, and that will give me 10.8. And this is also really important that you do have that value there to the minus 7 in this particular case. And we're going to divide it by our 0.02 molar, which is our NH4 plus, and our 0.2 molar, which is our other guy. Molarity and molarity going to cancel, and we will end up with 2.7 to the minus 4. And again, the units here are going to be 1 over molar seconds. Any questions on that calculation, where any numbers came from? Now, I know in the few examples that we did here, everything came out to be sort of 1, for example, for each of these orders. And it won't always be that way, you know. So just say, for example, uh, if you did it and let's just say that this one came out NH4 to the second order and NO2 minus to the first order. In this case, the overall order, if it did come out this way, would be 2 plus 1, which would be third order. And more importantly, where it really will affect, you know, sort of the calculation is now when we solve for K, if this was our rate law here, which obviously it was not for this particular example, if we solve for K, it equals the rate divided by NH4 plus squared times NO2 minus. So again, if all your orders are not 1, like it was in this made up example here, you do need to make sure that when you do solve for K, for example, you would want to square it in that case, you know. So again, just a heads up, although these few examples here, everybody came out to 1 in terms of the orders, they won't always come out to 1. So it's possible to get like, you know, 2. It's even possible to get 0, for example, right? So if you take something to to the 0 order, for example, while we're talking about it, if that was to the 0 order, right, something to the 0 equals 1, right? So, you know, it is possible to get 0 order as an X. And again, that would equal 1 as well. So, you know, that's another common one that sometimes will come about. Any questions on how to determine the rate law, how to determine the value of K, the units of K, or the orders? Okay, and again, remember, if you do have questions, feel free to ask them. So now we're going to get more into specifics and specific types of reactions and sort of how they come about. So before here in these couple of examples, you know, we found the value of the rate constant, we found the overall order of a reaction, and you know, it could be first order, it could be second order, it could be 0 order, which are the common ones that you come across. So we're going to start with first order reactions. And in a first order reaction, you essentially have one reactant really to the first order. Yeah. So the rate law would equal the rate equals K times the concentration to the first power, kind of like a decomposition reaction, right? One reactant making some products. And if we look at the value of K and we solve for K in this rate law here, we get the units of 1/seconds are reciprocal seconds. And that is really important to know that when you have a value for K that has units of 1/seconds, and it doesn't always have to be seconds, it's really 1 over some unit of time. So it could be 1/minutes, 1/hours, 1/years, 1/days. Usually seconds is a very common unit because in the laboratory, if we run an experiment, we're not usually sitting there for days or years, right? We kind of do it in seconds or maybe minutes or something like that. So 1/seconds is very commonly sort of thought of as the units associated with the rate constant for a first order reaction. But again, it can be 1 over some unit of time. And again, that's really important to know because a lot of problems, they will not in flashing lights say, hey, this is first order, this is first order. They'll just give you that value of the rate constant. And they expect you to know that from the value of the rate constant units, that it is a first order reaction. And we do have what is sometimes referred to as the integrated rate law for a first order reaction, and that is the natural log of A equals the natural log of A naught minus KT. This is sort of your final concentration. A with the little 0 is your initial concentration. K is your rate constant. And T here is actually time, not temperature. So it's actually time in this particular case. And what we see here, if we graph the concentration versus time, is we see that over time, the concentration starts to decrease, is what we would expect to happen. Now, usually in kinetics, we like to graph things more like what we see over here. And what we see over here is basically a straight line, that y equals mx plus b, right, which is your formula for a straight line. And if you take this integrated rate law and sort of rearrange it a little bit, and you take the natural log of A equals minus KT plus the natural log of A naught. This is basically the first order rate law written in the form of a straight line. This is y is equal to mx plus b. So as you can see on the graph on the right, on the y, we have graphed the natural log of a. On the x, it is time. Again, that's what the little t stands for, although it looks like my plus sign next to it, but we'll make sure it is the t. And that's what we see graphed over here on the x-axis. And what we also see is that from this equation, if you take the slope of that line, it equals minus k. So the slope of that line equals minus k. So if you graphically graph the natural log of a versus time and you get a straight line with a negative slope, you can take the slope of that line and figure out the rate constant. Because this is a negative slope, right? The slope is going to be negative, and that's why there is a negative here, which means your rate constant will be a positive number. Also, if you take the y-intercept would equal the natural log of the initial concentration. So graphically, you could actually sort of solve some information. And if you do graph the natural log of A versus time and you get that linear graph, it probably is a first order reaction. We will also see that there's a half-life equation that goes with first order, and that's the natural log of 2 divided by the rate constant. So for a first order reaction, a few important things are pretty much what I just boxed around here. You do need to know that the typical units that you see for the rate constant is 1 over seconds, or reciprocal seconds, 1 over some unit of time. You need to know the integrated rate law here. This integrated rate law will allow you, if you know the initial concentration and some time, to figure out the final concentration, or if you know the final concentration and time, the initial concentration, you can figure out how much time. So you can do a lot of things. So this is really the equation that relates how concentration and time basically are affecting each other. And you should know also the half-life equation that goes with a first order reaction. And there are a lot of problems where you have to use both of those equations together. And typically, sometimes in a problem, they will give you all the information. So they'll give you something like initial concentration, they'll give you something like the time, and they'll want you to figure out how much is left over. And the one thing that you'll be missing is the rate constant. So it's very common in kinetics problems that you have to use the half-life equation to get K, and then you'll have the missing piece that you would need, for example, to solve a problem. So there's a lot of problems where you sort of have to use both of those formulas together, and you know you need to do that, obviously, if you see you're missing something. The last thing that you should know as well is, in addition to the units for K, these two equations is the graph, the linear graph that is typically associated with a first order graph, which is the one on the right. Any questions on that there? All right. So here, reaction is first order with A. It has a rate constant of 2.8 times 10 to the minus 2. How long will it take for A to decrease from 0.88 molar to 0.14 molar? So why don't you take a minute or two and see what you come up with. Okay, so hopefully, let's see, can we hear? Just want to make sure if everybody could hear me. I hope now you can. Hopefully, yes. Okay, good. I just want to make sure. It was like showing I wasn't speaking or anything. So, okay, good. All right. So, continuing on here again, let's see how we did. Looking like you did good. So, we do have our rate constant here, which is 2.8 times 10 to the minus 2. We do know it's first order because they did tell us. But again, if we didn't, we could look at the units that we see here for our rate constant. And it is reciprocal seconds, which again, typically is our first order. So 0.88 is our initial, 0.14 is our final, and we are looking for t in this case, and we do have k. So that would give us the natural log of 0.14 equals the natural log of our initial minus the k, which was given to us in this case, and times t. So kind of cleaning up the left-hand side here, natural log of 0.14 minus the natural log of 0.88. And we're going to divide by minus 2.8 to the minus 2. And it does give us 65.65 in terms of seconds there. In terms of how long it would take for this reaction basically to get to that concentration. Any questions on that? So again, mathematically here, what I did was I took the natural log of 0.14. I then subtracted the natural log of 0.88. And again, if you did that, that got you minus 1.83827 equals minus 2.8 times 10 to the minus 2 times t. And then obviously I divided this to both sides. Those canceled, right? Along with the negative, which is how we got to our positive number. Any questions on that one there? Okay. Now, I sort of got to this before, but again, there is a half-life equation here that does specifically go with first order reactions, and it is the natural log of 2 divided by k. And the 0.693 is what you get when you put into your calculator the natural log of 2, and you get that 0.693. So again, the half-life is the time, like it sounds like, that it requires for half of whatever you started with basically to disappear. So again, if you started with 10, after the first half-life, you'll be down to 5. After the second half-life, it'll be down to 2.5. After the third half-life, I probably should find a calculator and divide by 2, but you get the idea. You keep going down by 2. So again, if we wanted to know what the half-life is, if it has a rate constant of 5.7 times 10 to the minus 4, we can use this equation here. And first off, we would take the half-life natural log of 2 over k. And since they gave us that, the natural log of 2 divided by 5.7 times 10 to the minus 4 reciprocal seconds will get us about 1200 seconds, give or take. If you did a little sig figs, 1216. If you didn't, the seconds would come to the top. Again, reciprocal seconds here. So when you divide it, right, the seconds come to the top and you'll end up with about 1200 seconds. If we weren't sure, how do we know we should be using the half-life equation for our first order? it is right here, the rate constant with the units of reciprocal seconds. Again, 1 over some unit of time is your classic key that it is a first order reaction. Any questions on that there? So obviously, first order reaction usually a lot of times will involve, not 100% of the time, but a lot of times involve one reactant to the order of 1. Like we said here, in a sort of decomposition reaction is commonly that. And here's our half-life. Again, after every half-life, we essentially will have half of what we started with left, probably around 10 half-lives in, pretty much gone at that point. So if you count the circles after each half-life, we do see it start to disappear. And again, we do see that decrease with time sort of graph that we see in this guy. All right, whoops. So why don't you try this one here? It's first order with rate constant given. Find the concentration after 865 seconds if the initial concentration is 0.0225. So see what you come up with. Okay, so let's take a look. So again, the key here, if not really told this first order, you can figure out it is first order here based on the units that we see. So again, we want to use our integrated rate law here. And again, this is specific for first order. In this case, we do have the initial given to us. We do have the rate constant. And actually, in this case, we have time given to us. So we do have everything on the right-hand side given. And we're looking for what's on the left. So that would give us the natural log of A equals the natural log of our initial, which was 0.0225, minus the rate constant that was given to us, which is 2.90 times 10 to the minus 4 reciprocal seconds, and times our time, which is 865 seconds. One key thing you do want to watch out for when you're doing these problems are the units here. The units of K and the units of time. In this particular case, we're okay because they're both seconds, but there are a lot of problems where they are different units. So at some point, you do have to do a conversion sometimes to get them into the right units. So if we clean up the the right-hand side there, we will get the natural log of 0.0225 minus 2.9 to the minus 4 times 865, or gets us the natural log of A equals minus 4.04508.997. Feel like writing a whole bunch of numbers. To get rid of the natural log, though, we do need to take the e of both sides. So you're going to take the e of that guy. You also want to take the e of this guy here. When you do, basically the natural log goes away there, and that leaves you with the a. And if you do that there, you do end up with 0.0175 molar, and we would need the concentration there, as that's what we're solving for, and it would be the same units obviously as our initial. And we should also make sure a couple of things. What we started with is more than what we ended up with, right? Because we are basically decreasing with time. So if we ended up with a larger number, that would not be good at this point. Any questions on that particular one? Okay, we're going to skip this example. Let's talk then about second order reactions. So in a second order reaction, it's a little bit different. Some of the equations and graphs that we see associated with a second order reaction. So first off, in a second order reaction, one way that we could get that is with one reactant that has an order of 2, and that would give us a rate law such as this. The rate equals k times a to the 2. And if we solve for k in terms of units, one of these molarities and one of these molarities will cancel out. And we do get the typical units that we associate with a second order reaction, which is 1 over molar seconds. So just like the first order, where it's 1 over seconds, which is a common unit, 1 over molar seconds is also a common unit. But the seconds part of it does not necessarily have to always be seconds. Again, it's some unit of time. So it could be minutes, hours, stuff like that. But it's 1 over molar times some unit of time. Now, there's also a rate law. Our integrated sort of goes with it, and it is this one specifically for a second order reaction, is 1 over A, which is our kind of final concentration, equals 1 over A naught, which is our initial. And again, the K here is our rate constant. And just like in the previous one there, the T is time. So it also has a half-life equation, which is different than first order, and it is here. And the half-life of a second order reaction is 1 over K times the initial concentration, which means unlike the first order reaction, the second order's half-life is dependent on the initial concentration that's there. Now, we could also rearrange this equation and write it as 1 over A equals KT plus 1 over A naught. And this would be y equals mx plus b. So the typical graph that we see, the linear graph that we see for a second order reaction, is on the y is 1 over the concentration. On the x, it is time, just like it was before. And in this particular case, we will actually get a positive slope in line. And the slope in this case would equal the rate constant. As you can see here, the slope equals the rate constant, while the y-intercept would equal 1 over the concentration of A. So just like our first order reaction, there are a couple of important things, obviously, that you should know for a second order reaction, which again can be achieved by one reactant to the order of 2. It also can be achieved by 2 reactants where they each have first order, which is what we saw earlier. Each of the reactants had an order of 1, which gave us second order overall. Now, you do need to know the typical units for a second order reaction in terms of K. You also need to know the rate law for the second order, and obviously as well the half-life that goes with it, and the typical linear graph that's associated with a second order reaction. Any questions on that? Now, the last type of sort of reaction we're going to talk about in terms of rate laws is a zero order reaction. And a zero order reaction also has sort of its own set of information that you could use to determine it's a zero order reaction. So to get something to a zero order, that basically means that when you take something to zero, as we talked about a minute ago, it equals one. So you could have a reactant to the zero order, which will give you the rate law, where the rate will basically equal K. So the way that you can recognize a reaction as being zero order is if you have a rate constant that has the units of molarity over seconds or some unit of time. And again, that tells you automatically that you're dealing with a zero order reaction. And the zero order reaction is very similar to the first order in terms of the integrated rate laws, except that there's no natural log. So this is A equals A naught minus KT. And that's your equation for how concentration and time is changing. The half-life is equal to the initial concentration divided by 2K, which means also here the half-life of a zero order reaction is dependent on the initial concentration. When we rearrange this equation, very much like what we did with first order, take the concentration of A equals minus KT plus the initial concentration, that is our Y equals mx plus B. So you can see on the graph, on the Y is our concentration. On the X again here is our T. And the slope here, just like first order, actually equals minus the K value. You may also recognize this graph as the one that we saw in first order, but there is a difference between the graph that we see here, that was the concentration of A versus time, and the one that we saw for a first order reaction. For a first order reaction, it is not linear, it's decreasing with time. And again, that is first order when you have concentration versus time and not a linear graph. But if you graph the concentration versus time and you do get a linear graph, then it is a zero order reaction. So just like the others, for zero order, the units associated with K is important to know. The rate law here for time and concentration, half-life equation, and the graph that's typically associated with a zero order reaction. Okay, let us take a look at this one here. So see what you come up with and work on it for a minute. I'm just going to stop sharing for just a second. I'll put it back up in just a sec. Okay, so let's take a look. So here it says the second order. So we do want to use the correct equation, which is this guy, 1 over A equals 1 over A naught plus KT. In this case, we're looking for K, and we do have our initial and our final. So remember, our final is the smaller guy, so 0.001 equals 1 over our initial, which is 0.01, plus, again, this is the only ones that are plus, K, which is what we're looking for. And there we have our time, which looks like 500 seconds. So here we want to take basically 1 divided by 0.001. We're going to subtract it from 1 divided by 0.01. And that'll give us something like 900 equals K times 500 seconds. We then would divide it by 500, and we would get K equals 1.8. So what about units, right? Typically, this is 1 over molarity, right? And this is 1 over molarity, which means we technically still have 1 over molarity there. And we also divided by seconds, which means we do have 1 over molar seconds as our units here. So again, you want to keep track of those units. If you can't, the other thing you can remember is you already know that if it's second order, the units of K should be like 1 over molar seconds or something like that. So you can sort of add it in at the end there. Again, by knowing those units that are associated with those rate constants. Any questions on that? Okay. So this is a nice little summary sort of table of all the important sort of information from those different orders. Again, zero order, our integrated rate laws, and our half-life, our first in our half-life, and obviously our second in our half-life. And again, also very important in terms of kinetics is understanding those graphs that you expect to find. And sometimes people do experiments where they will basically try to figure out the order of a reaction by doing graphs. And they basically have to make each of those graphs. So they have to make concentration versus time for a zero order, natural log of A versus time for first, and 1 over A versus time for second. And basically they do a best fit line and they try to find which one is the most linear, right? And you can use something like your R squared value. If you use something like Excel, right? R squared value is that linear coefficient. And again, if it's 1, it means it's perfectly linear. If it's not so much 1, then not so linear. So it's a very graphical way in sort of kinetics that people try to determine the order of a reaction. Any questions on first, second, or zero order? So the next thing we're going to talk about then is energy and sort of what happens. Good talk. And sort of, let's go back. Come on. There we go. Maybe. All right. So these are two diagrams, and these are two energy diagrams. And the one on the left is an exothermic diagram. So I know we didn't talk too much about energy this semester here. We'll talk about it next. But exothermic basically means heat and energy is released. And usually delta H, which is the enthalpy of a reaction, will have a value of negative for something that's exothermic, while endothermic is the opposite. Heat and energy is absorbed. And the delta H value is typically a positive number for that guy. And one way when you look at an energy diagram such as this is when you see your reactants are higher in energy than your products, basically energy has to be given off, right, in order for those reactants to get down to the products. And that is your classic exothermic diagram. Opposite here, our reactants are lower in energy than our products. And that means energy has to be put in, basically, to allow those reactants to get up there to the products in terms of energy. And there is a hill that basically a reaction has to sort of climb to get to the other side. And basically for a reaction to take place, two things has to happen. They oftentimes has to collide with each other, collision theory. and they need to hit each other. Not only hit each other, but they do need to hit each other in the right spot. And they do have to hit each other with the minimum amount of energy that's required for a reaction to take place. So not all collisions when reactants come together will result in products being formed. Those two things are must. They got to hit in the right spot, have the right amount of energy for products actually to be made. Now there is this hill, which is known as the activation energy here. And that's abbreviated sometimes as E of A. And again, it's the hill that the reactants has to climb to get to the other side. And it affects the rate of the reaction. The bigger the hill to get to the other side, the slower the reaction usually. The smaller the hill, the faster the reaction is to get to the other side. As this reactions are happening, as this reaction are going, you are starting to break bonds. And as you kind of come this way, you're starting to make some bonds. And when you get to the very top of the hill here, you get this guy right here. And this is what is sometimes referred to as a transition state complex or an activated complex. And it is something that's very, very high in energy, as you can see. And one thing that you should probably know is higher in energy is usually things that are less stable, right? Things want to be in lowest energy. That's essentially what everybody wants to be in. So this is just the highest point you could get in terms of energy in this reaction. And that is what is sometimes referred to as a transition state or the transition state complex. And what that guy is essentially something that has partially broken bonds and some partially made bonds happening all at once. And usually very quickly, it will sort of make its way down the hill to the other side to make products. It's usually very hard to isolate because it's high in energy, not very stable, not very happy, and usually will go to the other side very quickly. We also see that in comparison of exothermic to endothermic, we do see that the hill that an endothermic reaction has to climb is usually much higher than an exothermic. Does sort of make sense because overall you got to kind of put energy into that reaction to help everybody up and over the hill to get to the other side. So there is a relationship in terms of temperature and the rate of a reaction. It was one known as developed by Lorena, who did a lot of work with electrolytes and things of that nature. And we get this relationship at K, which is our rate constant, equals A, which is a frequency factor. That's sort of the proportion of molecules that have enough energy to get to the other side. E to the activation energy. R, which is our gas constant. And it's actually the gas constant, not the one for the ideal gas law, but it is the one that involves energy. So it's the 8.314 version of it. And T here is actually temperature in Kelvin. And this is one version of the equation that relates basically the rate, how fast it occurs to temperature. In general, if we increase the temperature, usually the reaction will occur a lot faster. Again, everybody has more energy. There's a greater proportion of molecules that will have enough energy to get up and over that hill, basically to the other side, and vice versa. If you lower the temperature, usually the rate of the reaction will slow down because, again, you have a less proportion of molecules that have enough energy to get to the other side. Like we see here again with our activation energy. And as I mentioned before, again, what we see at the very top there is what is sometimes referred to as that activated complex. And that again is a guy that is partially breaking bonds, partially made bonds, and very, very high in energy. And again, doesn't like to hang around a very long time. So a different way that we oftentimes will sort of use the Arrhenius equation is in this form on the bottom here, where we kind of go through and take the natural log of everything. And the way this guy is written, this is sort of the graphical form of this equation. And that's because this is y is equal to mx plus B, which means the typical Arrhenius plot that we see is on the Y, we have the natural log of K. On the X, and we'll see this graph here in just a second, we have 1 over the temperature in Kelvin. And this will usually give you a straight line, where the slope of that line will equal minus E of A over R, which is what we have here. And also the y-intercept would equal the natural log of A, and you could use it to graphically determine the frequency factor. You could also see that typically this graph gives you a negative slope. Again, the negative and the negative here is going to give you a positive value for E of A. So usually the activation energy is a positive value when you do that, and you use that sort of graph answer. So here again is a typical Arrhenius plot. And again, you can see a negative slope. So if we took the slope of that line, it would equal minus E over A over R, which basically means to find the activation energy, basically the slope times R, which R is a constant, that 8.314 number. And it's very easy sort of, if you have the graph, to obviously find the value of the activation energy. That, by the way, when you do this, because R is in joules, this will give you the activation energy in joules. Usually, though, kilojoules is the value associated with activation energy. So sometimes you do need to convert it from joules to kilojoules. There's a lot of information about what we were just talking about, but essentially, sort of the take-home message here is that increasing the temperature typically will give us a greater proportion of molecules that's able to get over that heel to the other side, and vice versa. Obviously, lowering the temperature will do the opposite. And all of it, obviously, if more guys have enough energy to get to the other side, we would expect an increase in the rate of the reaction, and vice versa if we sort of lower the temperature. And that's what we see here in this graph, T1 versus T2. T2 is a higher temperature. And what we see is, and if this is our activation energy right here, for the higher temperature, we have a greater proportion of molecules that have gained enough energy basically to get over to the other side. Thus, at the higher temperature, we would expect the reaction to occur faster. In case you missed the first 3 times we saw this equation, okay, one more time for you. So here's a typical sort of table that you would be given, for example, in a problem, and you may be asked, obviously, to do a plot, probably not on the exam, but in real life, if you were doing some problems, for example, out of the textbook or something, you may want to use Excel to do this, but you're given the rate constant for each of these guys, and you're given the temperature. So essentially what you would have to do is you would need to go through and take the natural log of K for each of those values. You would also need to go through and take 1 over the temperature. It happens to be in Kelvin already, so you would be good on that. And then basically you would make that plot of the natural log of K versus 1 over the temperature. And again, it would yield you that straight line. And if you did that, I believe we have the graph here for us, which is really nice. And from this graph, again, we could use the equation for a straight line, which you could get from something from Excel. And if we want to know the activation energy, E of A would equal basically the slope, right, equals E of A over R. So E of A would equal the slope times R, and also our negative there. So the slope that we see here is a negative slope, like we talked about. So E of A would equal minus 1.12 times 10 to the 4 times 8.314. And that would get us something like 93116.8. Because of this guy, the units are joules. And if we want kilojoules, which is typically what activation energy is given in, something like 93.1 kilojoules. Again, here a positive number is what we would expect. In addition, we can typically find the frequency factor. And remember that from that equation, the natural log of A is equal to the y-intercept. So again, if we go back and take a peek here, where did I go? Right here. So this is B right here, which equals the natural log of A. And if we do that, we see that the natural log of A equals our y-intercept of 26.8. We would take the E of both sides. And that would give us an A value or a frequency factor of 4.36 times 10 to the 11. The units usually associated with the frequency factor are usually the same units that we associate with K. So this would be molarity seconds, 1/molar seconds. Any questions on how to use the graph and the information from the graph and the line to figure out activation energy are obviously the frequency factor. And again, that's a very common way, and hopefully they got the same number as we did, I hope. Yeah, so that's good. Good deal. Could just flip the thing. And here it is in a much prettier form when we did that. Now, a lot of times, though, we don't want to make graphs. So there is what is sometimes referred to as sort of the 2-point version of this equation. And this is one where you could sort of mathematically solve for a variety of things. You could find the rate constant, you could find the temperature, the activation energy, if you wanted to. Now, when you use this equation, you definitely want to watch units here. Again, this is typically kilojoules, R is joules. So you do have to do some type of conversion. Otherwise, again, you're going to be off by a factor of 1,000. This is 1/temperature. These also do need to be in Kelvin. And there are actually like 3 different versions of this equation. Some people will kind of distribute the minus out and do like, 1/T2 minus 1/T1. Some will combine it and do a combined sort of thing with the temperature. So this is one version of it. If you look somewhere else, you may see a slightly different version of it, but it usually involves some negative signs being sort of distributed and these guys sort of being switched around and stuff like that. So why don't you take a moment here, so we'll finish up hopefully here with this and see what you come up with. Find the activation energy given this information. Okay, let's take a look here. So again, we're not going to graphically do it, so we'll use the equation there that we saw. So that is K2 over K1 equals A over R 1 over T1 minus 1 over T2. So again here, we do want to make sure a couple of things. Excuse me. The temperature is already in Kelvin, so we're good on that. And we are looking for the activation energy. So we have K1 is 2.57. And again, the temperature that goes with it is 701. Our K2 is 567. And our second temperature there is 895. So putting it in, natural log of K2, which is 567 over 2.57. And that is going to equal E of A, which is what we're for. R again is a constant. We make sure that you do use this one here that involves energy. 1 over T1, which is 701, minus 1 over T2, which is 895. And if we kind of clean up the left-hand side there, we end up with 5.3964 equals E of A over 8.314 if we clean up in the parentheses. And 0.000309. We're going to multiply 5.3964 by 8.314. And then we're going to divide it by the 0.0003 number. And that will get us an activation energy of 45095. Again, the units here would be joules based off of R, but activation energy, like I said before, is typically given in kilojoules. So if you divide it by 1,000, you get something like 145 kilojoules, which is good. And again, you do see a positive value for activation energy, which is typically what it is. Any questions on sort of the mathematical way of relating temperature to activation energy to rate constants? Okay, and I think that's a good place to stop for the season here. All right, so we will end there, and that is it in terms of lecturing. So you're responsible for up to here. There's only one thing left, which is mechanisms, so we won't get into mechanisms. But pretty much we covered all the kinetic stuff that I think you need to know. A reminder that on Thursday is our final, and it will occur at the start of lecture time. It is comprehensive, so it will cover all the chapters and all the material that we talked about throughout the entire semester here, including through this chapter up into what we talked about obviously today. So everything's sort of fair game in that sense. It probably will be a similar format to the rest of our exams. So it'll be probably the multiple choice part and then probably some written part as well. In terms of the lab, I think we are going to not do the very last lab, which is kinetics. I think they actually only filmed one part of it anyway, so there wasn't much to do. So we're going to skip the last one, which was the kinetics experiment. So really the last one, hopefully you turned in, I think by now. If not, make sure that you do. Should be the boiling point one, if I'm not mistaken, which was the pre-lab and post-lab questions for that one. So that should have came in, I hope, by now. The final may be a little bit longer than regular exam. I'm not sure yet. I haven't written it. I guess that's what tomorrow's for, right? And but I don't know if it'll be tremendously longer, but it might be just a tad longer again. There might be some questions that obviously we might cover multiple topics that sort of go together, I guess is a way of putting it. Um, so there'll be that kind of stuff. I don't know if you'll get much more time than you usually do. I think what you get is probably sufficient. So you'll probably have about the same amount of time. And again, I don't know if the exam's going to be that tremendously longer, to be honest with you. So I probably anticipate having about the same amount of time as what we've had before, a couple hours or so, whatever it is, something like that. Probably what you'll be given. Other questions on that? In terms of the homework for this chapter, you don't have to obviously upload anything. If you take the final, then you will get credit for this chapter in terms of the homework. I would recommend, though, that you do go through some of those problems again. Um, there may show up, obviously, on the final as well. Other questions on any of that stuff or anything else? I don't think we have anything else out there in terms of what you need to turn in. So I think really all that's left is really to take the final, if I'm not mistaken. Um, your exam scores and everything like that should have been uploaded yesterday and stuff like that in case you missed it. Should be up there. And I think that's about it. Yeah, I'll go back and open the last ones. I think I took them off first a second, but I'll open them up before the final so you can take a look at them if you want to kind of review the old exams and stuff like that. Other questions on any of that? All right. Well, congratulations on, finishing, right? You still got one more thing to go, I suppose, but pretty much finishing Chem 200A and not the best of circumstances. So you should be proud of yourself for hanging in there and continuing to come to listen to lectures and obviously participate in a class. And I did enjoy having you guys in person when I was able to see you and online as well. And I do wish you best of luck on all your finals, including ours. Uh, and again, so the only thing left again is on Thursday for you to take the final. And then I think that will be it. If you have questions, you can feel free to email me or anything like that. I'll be happy to obviously get in contact with you. I don't think there's going to be a lab session or anything like that. We really don't have anything to discuss, I don't think. And again, you could go use that time to hopefully study for the final. Any questions on anything else? Okay, well, have a good night, good rest of your week, and again, good luck on your finals that you have this week, and have a good rest of the summer if I don't talk to any of you guys again, kind of in person.